talk very much about Swift. I just want to give some idea of cosmological simulations and what I think some challenges will be. Yeah, and as you said, I'm mostly, I would think I'm a numerical cosmologist at heart that ends up writing code because that's how we make progress in the field. And I'll probably try to give you some flavor of this in the next 20 minutes. So let me just give you an idea of what I mean by that. So what I have here on the left is just a quote from this book by Zach Weinersmith, which we may know as, if you read the webcomic Saturday Morning Breakfast Cereal, who is summarizing sort of the state of physics these days, where he says, you know, Aristotle said a bunch of stuff that was wrong, Galileo and Newton fixed things up, then Einstein broke everything again, and now we have basically got it all worked out, except for small stuff, big stuff, hot stuff, cold stuff, fast stuff, heavy stuff, dark stuff, turbulence, and the concept of time. There's going to be a bit much to cover all of this in the afternoon. I think concept of time will leave for another meeting. Probably the next speakers will have much more to say than me about turbulence. And in a good cosmologist fashion, I'll take all of the other stuff and put it in one single bag and try to talk about this. And so I think what he means here is that, you know, we have a sort of a general model where we understand the whole universe based on some 4 pillars of general relativity, quantum field theory, a standard model of particle physics, and our sort of a lambda cold dark matter model to describe the evolution of the universe. But there are some glaring holes in there. There are things we know are wrong, but we don't really know how to move beyond that. And that has been the case for some time now. And there are some very open questions, some of which could be, for instance, the difference between the predicted and the observed mass of the neutrino particle. We don't know what dark matter is. We don't have a theory of how gravity can be quantized. We don't know what the axion particles are that were predicted already in the 60s, and so on and so forth. So there are some really open questions here in just fundamental physics, which relate to cosmology, that we definitely want to answer, and we would like to make progress on as a field in general. And then for the astronomers in the virtual room, there are also plenty of questions just based on galaxy formation that we would like to answer. For instance, how do galaxies change shape? How do galaxies change color? What is the role of magnetic fields? What is the role of cosmic rays, which are these charged particle ejections? How many photons escape galaxies? How did, you know, where are all of the metals, which is what astronomers call every element heavier than helium? You know, what drives the formation of stars? How do massive black holes form, and so on and so forth? So all of these questions are tied together, and many of them rely on simulations. And so one thing which is quite different in the field of cosmology and astrophysics from other normal scientific method is that we don't really have a way of going into a lab, constructing a fake universe and testing different theories. We actually, you know, we only have one we can observe. So the next only thing we can do really is to simulate what we think is the truth and see whether it matches. So the numerical methods are there, really at the heart of what we can do. We don't have a lab where we have a fake star, or, you know, a lab star or a lab galaxy that we can test our theories on. And so, for instance, you know, if you take the whole universe, you can ask the question how you go from the left, which is an image of the universe very early on after the Big Bang, to the bottom right, which is an image of the distribution of matter in the universe at the present day. How do you go from the left to the right? And you have all of these different models. You know, I mentioned lambda CDM before, but what is dark matter, different model of dark matter? Do you have a variable speed of light? Do you have, you know, dark matter that interacts, dark matter that doesn't interact? Things like this are questions that are still somewhat open. And so in other ways, you could ask, what should our computer scientist here, what should she put in her system to solve this equation to go from the left to the bottom right? And maybe she can come up with an answer to you know, all of these question marks we have on the slide. One thing that is also important to notice is that there's a big range of scales. So early days, the universe is extremely uniform, which means that the density fluctuations are very small. But nowadays, they are really, really large, which means that the normal tool of physics, which is perturbation theory, and, you know, you always joke about spherical cows in vacuum. Well, all of these techniques that people usually use by assuming everything is a harmonic oscillator doesn't work anymore, because it gets very, very nonlinear very quickly. And so simulations of the full physics model are the only option. And just an example of how this works, and that also relates to Durham, where this meeting was supposedly to be held, is that this seminal paper from the mid-80s showing on the left results of simulation of a cold dark matter model, and in the panels with the blue label model with hot dark matter models, and the top right being actual universe. And this kind of simulations already 4 years ago were demonstrating how we can eliminate models that don't look like the data at all. And so the story is still the same. We want to make statistical models, large ensemble models, matching into the data and learn something about all of these open questions. So how do we simulate the universe? Well, I said we have sort of initial conditions are more or less known from this observation of the very early universe. I showed this sort of football, like rugby ball on the 2 slides ago. And then from there, then we add some boundary conditions. We usually have periodic boundary conditions to mimic an infinite universe. And then in forces, well, what is the physics that we want to add? So, the basic components are always gravity. There's some hydrodynamics. Then magnetic fields are coming more and more standards. People also like to add radiative transfer, which is the usual term for interaction between light, photons, and normal matter. Cosmic rays, which is charged particle transfer, usually following the magnetic fields. And then on the right, I have listed some constituents that are typically part of the simulation. So you have dark energy, which is essentially the box that means the stuff that makes the acceleration, the expansion of the universe accelerate. Then we have dark matter, which is completely this unknown substance that acts gravitationally. Normal matter here would be mostly gas, compressible gas. And then we have stars, black holes, neutrinos, dust, planets, comets, moons. All of these are currently treated mostly as subgrid models, at least in cosmological simulation. And from top to bottom, it goes from very easy to very hard to simulate by adding more and more physics, but also by adding more and more resolution. The more resolution you add, the more physics you will need to add to your model, as well as just more resolution elements. And for the SPH fans in the room, many of these can actually be done via SPH. So the gas is the obvious target, but then also radiative transfer, magnetic fields, and cosmic rays all have SPH-like implementation or implementation of top of the SPH method. And SPH is also ideal given that we have all of this resolution and this density contrast differences. And so having a Lagrangian adaptive method is also key. Now I mentioned the problem of resolution, and that may be slightly of a technical slide, but what I'm showing here is sort of the distribution of gas in one of our simulations at the very end. And so on the x-axis, you have the density. It's always a log, so it's astronomy here. So we're doing log-log plot. So you have the density of the gas on the x-axis. You have temperature on the y-axis. And then the blob is essentially the gas resolution elements in our simulation. For the astronomers in the room, I've labeled some interesting regions. But the key bit here is that there is a resolution limit below which we can't go, which is a diagonal in that plane. Because if you go below that, you have something which is too cold and too dense, and it basically will continuously collapse under its own weight because it will just, gravity will overcome pressure, which means that it's impossible to track in a simulation. Right? Your resolution elements would have to become smaller and smaller and smaller because gravity wins over all of the other forces. And so that gives a natural limit where we can say everything on the top left can be fully simulated, mainly by gravity and hydrodynamics, and everything on the bottom right has to come in the form of a subgrid model. And then the goal, of course, the name of the game in the exascale era and so on, is to move this diagonal further down towards the bottom right until we, get it out of the picture. And to some people, what is extremely worrisome is that the big circle I've labeled on the bottom right is where most of the action is in terms of forming stars, forming black holes, explosions of star, and most of the action is there, which is at the moment very often treated only in a subgrid fashion. So subgrid fashion is always a bit worrying to some people. I like to refer also to sort of weather forecasting, which is very similar. So I don't have a map of the UK. I picked a map of the Netherlands on here, but saying that they do very similar things to some extent in a very broad picture. Clearly, they are not simulating every raindrop. And I can tell you there's a lot of them here in Netherlands. So what they do is that, you have a typical cell of about maybe 1 kilometer in your resolution grid. The raindrops are about 1 millimeter in size. You also have a factor 10 to the 6 in resolution difference between where the physics takes place and what you simulate. And so I'm no expert there. in all of the details, but there's also a whole network of subgrid model to model how rain, fog, clouds, thunder, tornadoes, and other things happen below that scale. Now let's look maybe at a simulation. So this is the formation of a region of the universe. What you see here is the gas colored by temperature, and then the luminosity is the density. So cold is red, what will become white is very, very hot. And what you can see is sort of a network growing up, which we call the cosmic web. But the other thing which is important to notice is that we have these explosions that you can probably see where matter gets ejected away from this web. And why is this important? Why is this important? It's because it means that, you know, gravity is the dominant force, which means things become smaller and smaller. So you could imagine a system where you could just take a simulation, run it for a while, and then you have a smaller region and start a new simulation on a smaller scale, and then start a new simulation on a smaller scale, so far and so forth. And so, you know, and keep going until you reach the resolution you want. The problem is that because of some of the processes that happen in astrophysically, what happens on small scales backfires and feedback into the larger scales and makes these really large bubbles, meaning that you can't decouple the scales in an easy way. Right? Give you an example here taken directly from data. This is taken from the M87 galaxy or the Virgo cluster. On the top left, you have a really large view of that cluster in X-ray. And the bubble you have here is very similar to the bubble which was shown in white in the movie. If you now decrease the scale by a factor of 1,000, you see the galaxy in the center here with a jet. And if you decrease this by another factor 10,000, you have this black hole picture taken 2 years ago, which is sort of the picture of the black hole at the center of this galaxy. And what is happening around that black hole on these scales, which is 10 million times smaller than what happened on the left, is what drives these big winds. Right? And so we have this factor 1,000,000 between the left and the right here, at least, that we need to sort of resolve if you want to capture all of the physics at play here. But the factor of 1,000,000 in length scale also means a large factor in time scale. And I can make it even worse for you in saying that the jet you see in the middle panel here is actually hot plasma made of really charged particles flying at almost the speed of light. So not only you have a high density and you have really small scales and really short time scales, you're also having to deal with charged particles at really, really high velocities. So it goes beyond your typical Courant condition, for instance, for fluid dynamics. As a side note, we're talking about exascales. So maybe it's, you know, we didn't specify in what scales we're talking about. This middle picture here is about 50 exameter in size, for those of you that like more common units instead of the more astronomy-related parsec scales. Now, as I said, here's your ultimate challenge for cosmologies. The range of relevant scales is more than 10 to the 10. The range of relevant time scales is more than 10 to the 12. If you take the age of the universe and you say that these black holes vary on a time scale of a day, range of relevant densities is more than 10 to the 20. And then what we want to do is combine this gravity with fluid dynamics, with magnetic fields, with light propagation, with charged plasma. And then when we have done all of this, then we can go back and say, oh, let's now do this fundamental physics problem and change the fundamental laws, right? And try to understand something about the bits we don't know, like neutrinos or axion particles or modification of the laws of gravity. But we need to have all of this under control in some ways. So if I just go the rough calculation and say I'm going to use a uniform grid with a uniform time step, and I'm very, very good at computing because I can do any operation on any resolution element in one flop. I'm a very good computer scientist. I'm a very good HPC practitioner. And I divide this by 1 exaflop machine. I still need 10 to the 24 seconds to complete my simulation, which is 1,000,000 times the age of the universe. So clearly that's impractical, and we will need a lot more than exascale or zetascale or yotascale. And so that's clearly unrealistic. But obviously my calculation here is just plain wrong because we're not doing that anyway. We're not using uniform grids and uniform time steps. So at least on the spatial scale, this has been done in many, many places, is obviously the standard techniques of multi-grid approach, like adaptive mesh refinements are common, or things like particle splitting approaches or semi-Lagrangian techniques like SPH, for instance, are the classic tools to tackle this. And already with this, we can reach a ratio, the current simulation like the one I showed you before, the movie I showed you before, already have sort of a ratio of 10 to the 6 between the volume we simulate and the smallest wavelength we can resolve with our SPH particles. So that's not 10 to the 10 yet, but it's already 10 to the 6, thanks to these multi-scale techniques. Now, these multi-scale techniques have obviously some challenges, right? The load is not only, the load balancing is one. The load is not going to be is not just spatially variable, but also time evolving, right? So if I come back to my map of the Netherlands where I do the weather forecasting, the Netherlands doesn't change shape very often. I mean, every so often they build a new polder, but you know that still means I don't have to remesh every time. But here, the mesh that I need to evolve my simulation on changes over the course of my simulation. So I can't just do a pre-meshing in a pre-processing stage. So we need dynamical approaches. I'm a big fan of task-based parallelism, which we use in our code, with work-stealing approach, so that you can sort of dynamically evolve things as they go. Another option, which can be orthogonal or combined, would be to have sort of genetic algorithm where the domains evolve in sort of an organic way. That's also an interesting combination of things that could be tried out. And the other aspect is that a lot of, the more complex you make your code, the more time you spend in the logic of first deciding what to do, but also navigating the memory to access the bits of codes or access the bits of the domain which are doing something, rather than just raw flops. Right? You can, the obvious example here, you can think of a tree code versus an n-square loop of the particles. The n-square loop over the particles for the gravity would be really beautiful to do on a GPU, a lot of flop, everybody will be very happy, but it's still a lot less efficient than a tree code. But a tree code requires other operation than just the raw flop. So data movement and bandwidth become also part of the bottleneck, at least at some point. Now, the other aspect is that I just, in my calculation before, say, well, we are using a uniform time step. And again, this is something that people have not been doing for a long time. People have, in astronomy at least, and many other fields, have not done that. And we're already doing particle time stepping, usually in sort of a block system where you have particles on short time step, and then particle on twice as long a time step, and particle on 4 times as long a time step, and then you move in sort of lock sync. And then the idea is that on the shortest time step, you only evolve the regions which are interesting. So if I take back to my black hole image before, you could do the black hole every step, but then the stuff which happens far away from that galaxy, where the time scale where things change are a lot longer, you could do it every 8 step, every 16 step, every 1024 steps, and so on. And obviously you have some criterion to decide when to do what. So that's not new. This is what we've been doing as a field for a long time. But then the load balancing is still, it becomes a space-time problem, and it's still very difficult. What I'm showing here is an example from our code again, where I'm showing a strong scaling of a simulation with a large density contrast, just doing gravity and just gravity and hydrodynamics. So it's a strong scaling test where I'm increasing the number of threads on the x-axis and the time to solution on the y-axis. And if your code is perfect, it would be lying on one of these dashed diagonal. You have perfect scaling. In a fixed time step case, in pink at the top, I have somewhat of an okay scaling. And if I do this multi-scaling, this multi-time step system, where I only update part of the domain when my cool-run condition, say, demands it, I have this lower curve, which is a lot faster. It's more 100 times faster code, but it scales a lot worse, right? So if you measure how good your performance is in terms of scalability, whether it tells you, are you allowed to go on my Exascale machine? No, because your code scales poorly. That's not necessarily the best metric, because actually I'm doing the same simulation a lot faster than you, but I don't have that nice shiny plot on a diagonal here. They ask the question, why is it worse at scaling? Well, one reason is because here, the numbers on the plot are actually the average number of resolution elements that we update every step. And on the right here, what is happening is that I'm actually having, on average, fewer resolution element updates than I have cores on my machine, right? So there's no way that can ever load balance or scale very well, right? So what do we do about this? Well, either we make Exascale not being about more parallelism, but we make faster cores, and that's obviously not going to happen. Or we actually have to go to the next stage, which is to say we need a fully time decoupled simulation, where you need to process different regions of a simulation at different speed. You could think as being in the same way. If I come back to my black hole business from before, you could say I could give the first 1,000 black holes in my simulation to the first 1,000 cores, and they do the very small steps. And then the rest of the simulation I distribute over the remaining 1 million cores, and they deal with the longer range operations. And that's the hand-wavy way of saying it. The more formal way of saying it is that you can decouple the different wavelengths of the simulation and have them evolve separately. And then at some point you have a mechanism to reconnect them. Now, this comes with immense challenges. First of all, we need to formalize this mathematically properly, showing that at least mathematically it should converge, and it does converge. And there is some work already that can be done for this when you have a proper, nicely Hamiltonian system. People have demonstrated this is possible. Computationally, well, we need to load balance this in space-time. That's not going to be fun, you need to be able to shuffle data around your system. And then, on a sense of the hardware, is that this is inducing an extra new layer of extra logic of deciding what to do where, communicating. And so we'll need hardware that efficiently deal with the associated data movement and not only flop operations. So we need to be able to do more on that front as well. And so to conclude, I will just say simulation at the heart of cosmology developments. They are the one critical tool that let us make progress in that field, also in terms of fundamental physics questions that we want to answer. The scales in space and time that simulations span are immense, but also are completely non-uniform, which is a very challenging problem, which means that we need adaptive methods and also new numerical algorithms so we can enter the exascale era, because we're not just going to do a unigrid simulation. It's not going to bring anything. And then if I can make a request, please make hardware that also can be focused on the non-flop components so that we can actually make use of this method that we are trying to develop to make progress. And I think I'll stop here. And if there are any questions, I'll happily try to answer them. Thank you very much.
Thank you, Matthieu. So if anybody has any questions, please do type them into the Q&A. In the meantime, I think Richard Bauer may have a question.
I was going to jump in and ask you, Matthieu, what worries you about these new exascale machines? So Simon talked about those architectures. What do you think are the biggest challenges of the current architectures?
Yeah, I think the data movement and the problem of doing something which is not just flop, right? And I think this is not just us. I think it's a common theme. I know GPUs are very good also because they solve the same problems a lot faster and with a lot less energy. But I don't think they can necessarily do everything, right? The example is already from what we see. We do particle-particle interaction, but sometimes we have to fish out one particle out of a million to be the one that does the interaction on this specific time step. How do we do this efficiently? How do we come up with hardware that can do this efficiently? Maybe we need some logic to repack the data in the RAM, for instance, or things like this that reshapes the data in a way that we can feed it to the GPUs or whatever other accelerator you like and process it. Yeah.
Okay, thanks. So a couple of questions have come through. I'm conscious of the time, but I'll ask the three that have come through if that's okay. So I'll just do them in order. So the first is from Zhao Hu again. So he would like to know if we get space-time into the load balancing domain, what would you think the major requirements for current domain decomposition software stacks would be?
I don't know if it's a challenge for the software stack. I think it's at least my first impression, it would be it's a challenge to express the way we want to do domain decomposition in a way which is friendly to the software, to the possible software stack. I think you could say I want to decompose the amount of work equivalently between the different nodes, but maybe maybe I'm optimistic, but maybe all you need to do is sort of find the average amount of work over a sufficiently large number of variable steps and decompose that efficiently. But it may be more complex than that. So it's not impossible that it's doable with current stacks. For instance, you could imagine feeding your, if you're able to express your problem comprehensively in as a graph problem, then possibly the existing tools can already deal with it. For instance, like decomposing a graph efficiently.
The second is from Andrea Negri, and they ask, does radiative transfer modify radically the issues you pointed out in large-scale hydro simulations?
Yeah, I think, well, yes and no. I think the issues are the same, they just make them worse. In a sense that, you know, the speed of light is large, unfortunately, or maybe fortunately for many other reasons, but unfortunately for the computing side, it's large. So if you want to trace photon packets, then it means your time step hierarchy will be much larger. People nowadays, usually you do subcycling, so they will do hydrodynamics and gravity steps, and then in between these, they may do 1,000 extra steps of photon propagation. And so sort of they already have this decoupling between the two methods. You could see this as sort of an approach to code coupling. Maybe we should do this more with the other processes as well. But I think it's not at the really high level. It's not necessarily the most. It's not bringing in more new challenges, just making some of the current challenges worse. Mm. And they affect the physics, so it's very important that we understand how to do this efficiently.
Okay, thank you. And last is a double-barreled question.
Two for the price of one.
Absolutely, yeah. From Florina Kioba. So the first question, isn't load imbalance already of spatial and temporal nature? Why is this a harder challenge for fully time decoupled simulations?
Yeah, that's a good point. I honestly don't know, because we are not there yet with fully decoupled simulations. What I would say is that if you start with fully decoupled simulations, you will introduce some differences, because you try to even out the work by giving a few nodes, say the fastest time steps, and the rest of the domain the largest time step. So maybe you're actually making your life a lot simpler, but I don't know if you are making your life a lot simpler formally in the most general case, and how you will go about writing a generic domain decomposition methods to achieve that. But I think in practice, we haven't gotten yet there to answer your question and say whether it actually makes a huge difference. I think we'll know that when we try. But it's already spatial and temporal already, yes, in most applications, at least cosmology ones.
Okay, and perhaps the biggest question for last in some ways, what task-based programming model do you think will be the most successful for cosmological simulations?
Good question. So we use our own stuff, mostly because when we started, there was nothing that really worked properly. Also in link with MPI. I think I would second what the previous speaker said, and I think sticking to MPI is probably a good idea, because that's going to work, or at least people will make it work for us. And then what to use within the node, I think it will depend on your preference. I think, again, if you can stick to a standard, that's probably a good idea. So something like a HPX in C++, or maybe SYCL, or anything that is coming online and that will get support from enough vendors. If you're starting today, that's what I would do. Because then you're not on your own when a new hardware comes. Someone clever will make it work.
Isn't that the computer science mantra? Someone clever will make it work.
I hope. I mean, that's why. Yeah, that's what I hope. I don't want to write MPI. If someone clever writes MPI for me, that's very good.